Welcome to your alternative building materials video on bamboo. And bamboo is an exciting material to get to talk about because there's a history of research on bamboo at Santa Clara University. So bamboo can be used naturally in its form, creating these really beautiful artistic structures. It can be laminated more like a plywood to create more traditional building shapes. Here's some research on at Santa Clara University creating eye joists out of it. We'll talk about this a little more later. And then some fun stuff like using the bamboo culms to make a bicycle. So how does it work? Well, there's actually 1,600 species of bamboo. This is Dendrocalamus giganticus, and it is one of the largest growing bamboos. There are about 20 species of bamboo that are considered applicable for construction. Some of those are 4-inch diameter, but there's also some smaller ones that are solid all the way through that are very useful as well. Now, bamboo is a grass. It's very different from timber in that when you cut down bamboo, it grows back. And for the structural bamboos, on average, if you plant them in about 6 years, you're able to harvest something that would be adequate for construction purposes. But then every 4 years, you're able to come back and harvest them again. They grow back at about a 4-year cycle. So that's huge for sustainability. Also, for a single-family residence, you can get a significant amount more of bamboo out of an acre to build a home than you could get lumber. All right, so let's talk about some of the basic bamboo structure. So there's two types of bamboo. You have clumping bamboo and then the spreading bamboo, which is what most people think of. So the clumping bamboo, you have a main plant and then you get spurs that grow off of that. With the clumping or with the spreading bamboo, you actually will have rhizomes, roots that spread underground, and then you get new shoots growing out of that. And this is much like Bermuda grass. You can't get rid of it. Now, regardless of either one, you get the long stalks. The stalks are separated into two key sections, and that's the culm and the node. So the culm is the vertical section that exists between the two horizontal nodes. And so those are going to be terms we're going to be using. And when you are dealing with the culm section, typically it is hollow. It could be thick-walled or thin-walled, but typically it's hollow. Sometimes, though, it can be solid, and that can make a really great structural material. And so it's fascinating the way that bamboo grows. It actually, the shoot comes up out of the ground. The shoot already has, and you can see it both in this graphic image and then the actual underground photograph, it already has all the nodes established. So these will be all of your nodes, and as it grows, the space between the nodes stretch out and you get your culms. What's also fascinating about bamboo is that it comes out of the ground at its finished diameter. It doesn't get any larger. It actually grows inward, so it gets thicker by growing inward as it ages. And it's very fast growing. There are some bamboos that have been recorded to grow up as much as 2 feet in 24 hours. But like I said, for structural bamboo, it's usually about a 4-year cycle where you can harvest. Now, much like timber, it has a vertical vascular structure that adjusts and adds to its strength. And so in bamboo, which is different than timber, you don't have the tracheids. Instead, we have what are called these vascular bundles, which almost look like little flower heads at the top. In a vascular bundle, there's a close-up on the right, you're going to have these large vessels, which are used for transport of the liquids and the nutrients. They're surrounded by fiber strands that provide a lot of strength. And then the fiber strands are separated by the parenchyma cells, which also can give you some strength. But these are all oriented longitudinally, just like the trachea. So you get this longitudinal anisotropic behavior. And that's important when we look at the node composition. So what happens is in between the nodes, as I would head up my culm, I'm going to have these nice long cells. It's where my longest fibers and my greatest strength. When I hit a node, my fibers will turn to create the node, and I can actually have discontinuous fibers because they're turning, and new fibers having to start at the bottom of the node and continue on to the next one. And so your nodes are your weak spots, your strongest in the CULM area. Now, there are, as I said, 1,600 different species, but within the construction materials, there are two sort of champions, the mosos and the guajias. So moso is typically out of the Asia, China, there's a lot there, where your guajia, and specifically Guajia angustifolia, which is your key South American, primarily Colombia, Peru, that area, that's your South American bamboo. Now, in both of these cases, we can actually see those vascular bundles. So these little dark, almost looking like little flowers, are vascular bundles. And because bamboo grows inward, you have all your vascular bundles there on the outer, and they're spreading in towards the inner as it grows. You can see the guajia pushes larger vascular bundles out. You have more parenchyma cells and open space between your bundles in the moso. And in both of these cases, the guajia and the moso, the structural ones, these are the ones that grow at about 4-inch diameter, 3.5 to 4 for your preferred construction bamboo. This is just a close-up of how the vascular bundles vary with height. So this is really interesting. Your wall thickness is different the higher up you go. So the 18th internode between the 18th and 19th node, that 18th CULM, is going to be much thinner wall than the one that's 6th from the ground, because it has to support the higher weight, so it gets thicker and stronger. And you can see how the vascular bundles are grouped within these. And so you do have a variation in strength in your bamboo from the height, so where you're taking the bamboo out in the height, but also if you shave down at all the thickness of the CULM, if you remove the inner wall, you're removing the weakest material. If you remove the outer wall, you're removing the strongest material. And so it's very important when you're doing testing to note where in the length of the bamboo pole did you take your specimen, because ones from the top are weaker than ones from the bottom, and where in the thickness. All right, so how do we build with bamboo? So I just want to show you some cool examples, and then we'll talk about research we've done at Santa Clara. So this was actually put on for an expo. This is a really neat structure, but you can see very long bamboo poles connected together in a truss type structure. When we look inside, we can actually see some pretty heavy-duty connections that are having to hold it together, and they look pretty custom. Of course, they used bamboo laminates to create the furniture, which is pretty cool. Now let's take a close-up look at the connectors. And so what we'd actually see is they are stainless steel custom-made pins, so you can rotate on your pin. There is a threaded metal dowel that's embedded in concrete that has been poured inside of this. So it is a concrete filled with a steel bar that's being anchored inside. Now there's a challenge. When you put concrete inside a bamboo, the bamboo tends to swell, and then as the water evaporates out of, because it will absorb some of your concrete as water, and so then as that water evaporates out of the bamboo, you can get splitting and shrinkage. And so these ring clamps are put on to actually help with that splitting and shrinkage and expansion. So that's a pretty technical connection. Now that was bamboo being used as pure structural material itself. Sometimes it's used more as a architectural feature. So here the connections weren't as critical because it was actually being used for a exterior surfacing, sort of partway see-through, letting light through surface for a parking garage in the Netherlands. This was a rendering for it to be 7 stories. Here is its actual construction after phase 1 was completed, when you had 2 stories and a 3rd level deck. So we can see the bamboo there being used as your partitioning. So it's a nice use of that in a country where it does not grow. Now, challenges of connecting bamboo are one of the things that has limited its use and its acceptance. And so LAMBOO is a company that has laminated members together, much like a PEREIRA being really more of an LVL, the laminated veneer lumber, but taking long strips of the bamboo, gluing them up, and then you can create rectangular shapes that we're more familiar with connecting to get greater acceptance by the construction industry. And how might you get those shapes? Well, here's some images. This is from strand bamboo flooring, but it's the same basic idea. You actually have to run the CULM through this splitter, and then manually they're picked up, they're put into carts, and then they're spread out flat, all in the same orientation, a lot of glue, a lot of pressure, and you can get laminated layers, which can be turned into flooring, into Lamboo, whatever. Now at Santa Clara, we were really interested to see what we could do with bamboo, and the 2009 Solar Decathlon, Dr. Mark Ashheim led the design, and this was before Lamboo existed, of laminated bamboo I-beams that they actually built in the lab and tested, and then hired someone to build enough for the 2009 Solar Decathlon house. For the 2013 Solar Decathlon house, I-beams were created out of a bamboo plywood that weaved bamboo layers in a 45-degree angled mesh and glued it all up together. And then for the web, and then the top and the bottom flanges were actually made from solid bamboo. So the CULM was filled, but solid bamboo that was planed on two sides so that you could put it flush up against the web material, and then also have a flat top and a flat bottom, so you could set plywood on top, or you could set it carefully in a standard hanger, and the hangers are then just hung on a standard that looks like a 2x10, 2x12. And it was critical that these were sized and made the exact same size as existing TJI lumber. And so for a senior design project, Santa Clara students actually designed these, they built them, they tested them, they did the analysis that was required to put in the appropriate safety factors, and got this passed through not only the Department of Energy so that they could be used in the 2013 Solar Decathlon house, but they also had to have this approved by the Santa Clara building department, so it was pretty excited. They tested 8 beams, and they found a mean strength of 5,530 pounds with a standard deviation of 805. Now, the 6 standard equivalent TJIs that they tested in comparison had a slightly higher strength at 6,185 pounds, but with a higher standard deviation. And the demand was around 1,400 pounds because we wanted to make sure we had a strong factor of safety involved. Part of the team also looked at creating wall panels that could just be put in anywhere you needed 4x8 sections of walls. And instead of using regular plywood, they used the bamboo plywood. And instead of 2x4s, they used bamboo CULMs. And then finally, the top and bottom plates were laminated bamboo, turning it into a plywood that was glued up to create the equivalent of a 2x4 flat that could be used as the top and bottom plates. These walls were failing under compression at loads of 24,000 to 40,000 pounds. It was amazing, especially consider the demand that's shown there. Finally, there's been a lot of work at Santa Clara on low-tech connections. How do you just connect 2 CULMs together in places that can't afford that fancy connection that we saw in the EXPO building earlier in the presentation? And so here are 2 CULMs placed together, a fish mouth cut on the vertical member so that the horizontal member can nest into it, and then rebar bent in a U shape that's pushed up through an opening in the horizontal member, and concrete using to embed the rebar and locking it together with the number 3 horizontal dowel. So we attempted to test these in a machine that could test with a 10-kit pull, and we can already see where the bamboo was splitting due to the mortar being put inside of it, as we said could happen. There were no ring clamps or anything put on this to stop that. What we saw, though, was that through a series of tests, we always failed by the rebar pulling out, and that we had a pretty reliable failure of 862 pounds with a standard deviation of 47 pounds, and this was from 4 tests. Now, we thought this is kind of a difficult construction method, and we didn't like the 862 pounds. We didn't think that was enough, so we said, okay, what are some existing building materials? And there are companies that make metal strap that already has nail holes in it for timber framing. And we said, all right, and it comes on these long 200-foot rolls. Let's use some of this standard strap that we got from Simpson Strong Tie. And we had to use, normally you would nail this into wood. You cannot nail into bamboo. The outer CULM is so hard because it actually sucks up sand and silica from the soil. It's hard on tools, and if you try to nail it, it will split. So we used tapping screws that you would normally use for sheet metal construction or cold form steel construction. So they pre-drill a hole as they're going in and then the threads catch. And we did the same pull test. What we found was a very reliable failure, and we were trying to make sure the failure happened in the metal or the screws every time, since the bamboo is organic and less likely to have consistent material properties. And we found that basically the strap yielded on every test we did when we had 8 screws into the vertical bamboo members, so 4 on each side. The strap consistently yielded at 3,860 pounds. If we only put in 2 screws each side for a total of 4 screws, then the screws were pulling out and yielding at 616 pounds. So that was very exciting to be able to use the 8 screws and get this very high consistent strength. So how would we get something like this into the community and get it accepted? Well, we've read about this in our papers on how we can use alternative building materials in developing countries. And these 2 gentlemen here are actually both founders of schools and programs in different countries. The one on the left is working with Eco Bamboo in Colombia, and on the right we have in Thailand the CHIANG Life Construction. There they are in Colombia in front of the Eco Bamboo's storage area where they store all their different structural bamboo that has been graded, where they've created a grading system just like you would grade lumber. Now in Colombia, the Eco Bamboo founder has gone about building a number of beautiful bridges to bring the community back into bamboo, to make it socially acceptable, to show that it's a beautiful, strong, resilient material. And his school actually trains carpenters to be bamboo expert builders, to start trying to bring this very cost-effective building method to the poorer of the population. In Thailand, you have this amazing school, and so the Chiang Mai school was actually built out of bamboo to show it off. There's all these beautiful buildings. This is the interior with the bamboo actually embedded into huge boulders to create the structure. And they've used also cob construction as some of the infill walls. It's a very fancy system. As our speaker Anthony Dente was talking about, you get creative people, you get creative shapes. But what they also teach at that school is how to treat bamboo and deal with bamboo. Bamboo needs treated just like wood does for pests, insects, and decay. And so they typically soak it in a borax solution, which helps stop the insects and the decay. This is only if it's left outside. If it is integrated into walls, it's just like wood, it can be protected. So finally, bamboo is, like wood, an anisotropic material. It is not wood though, it is a grass. It is very strong for its weight, often being heralded that it's so much stronger than steel, but really what they mean is the strength to weight ratio is greater than steel. We have done compression tests on Guaja angustifolia CULMs in the lab, just little short compression ones where we're yielding, and we've had as high as 14 KSI. Y'all were designing 4 KSI concrete, so that's pretty exciting. There are 2 places where you can get some code information. There's IMBAR, which is working hard to get codes out, but they have useful construction techniques and strength values. And then Colombia actually has its own building code for bamboo. So this is your intro to bamboo as a structural material. There's a lot of opportunities in this field, and I encourage you to spend some time checking it out. Thanks for watching.